So in talking about energy, we can classify it into two major types. We have kinetic energy, which is the energy that is associated with an object when it's moving, but an object can also have energy even if it's not moving. This is energy that is stored in some way, and it is called potential energy. We've talked about some different types of potential energies already. Gravitational potential energy is energy stored when an object is raised to some height. Elastic potential energy comes stored in a stretchy material, such as rubber band. And when we stretch or compress a spring, we say that the energy is stored as spring potential energy. There are also some other potential energies, such as chemical and electric and thermal, that we might get a chance to come back to later on. Our first focus is going to be gravitational potential energy. We know that the amount of gravitational potential energy stored in an object has to do with its height above a surface. So to do this, we are simply going to raise a mass above the surface and figure out how much energy is stored in it. You'll need two partners to perform this experiment. One of you will be in charge of taking data in Logger Pro. One of you will be in charge of holding the force sensor and the mass steady so that we can take data in Logger Pro. And the third person will be in charge of measuring the height of the mass and converting centimeters to meters. If you were not here while we whiteboarded the lab, you definitely want to get with your partners and you want to see what notes we took while we did that. So now we want to annotate our graph. This graph took quite a few of us by surprise because when we raised the mass, the force of gravity did not change. But really, if you think back to our unit on force, where we discussed the force of gravity, it shouldn't be too much of a shock because the force of gravity does not change significantly anywhere on Earth. Gravity always pulls down with a force equal to 10 times the mass of our object. So the rise on our graph represents the change in the force of gravity, which we know to be pretty much zero. All right, so what about the run on our graph? Our run represents how high we have raised the mass. Remember that little triangle delta? It means change in. So we have the change in height of our mass represented by the run on our graph. Now what about the slope? Slope is the rise over the run of the graph. So in this case, the change in the force of gravity over the change in height. But we just said that the change in the force of gravity was zero. So what does this say about our slope? Well, our slope is zero. Look at our line on our graph. It's a horizontal line. There is no slope. So what this means is that the force of gravity does not change when we change the height of our mass. Of course, this sounds familiar because we just talked about there not being a change in the rise on our graph, meaning the force of gravity doesn't change. So now let's look at our y-intercept. Remember, the y-intercept is where the line on our graph crosses the y-axis. Notice this particular line does not cross at y equals 0. It crosses at some value. Okay, so what does this mean? It means that when the mass is at 0 height above the surface, there is still some force of gravity acting on it. This makes sense. We are, after all, still on Earth. So there is always some force of gravity acting on our mass, no matter how high above the surface it is. Also keep in mind that, like we have talked about with the rise and the slope, the force of gravity is the same everywhere. All right, so now we want to look at something a little different. In some of our graphs in the past, we have used the slope to define new properties. Remember our position time graphs where we said the slope described the velocity of the object in question? Well, this graph is measuring the force applied over some distance. And on a force distance graph, we can take the area underneath the line and define a new property of our object. So let's look at this a little closer. What shape is formed between the x-axis and the line of our graph? It's a rectangle. And how do you find the area of a rectangle? You take the width times the length. Okay, simple so far. What is the width on our force distance graph? The width is actually representing the amount of force due to gravity. All right, so what's the length representing? The length of our rectangle is the distance the mass traveled, or in this case, the height above the surface. So the area under the line of a force distance graph is found by taking the force times the distance. This gives us a label of Newton meters. So what does that mean? Well, if we apply some force over some distance, maybe that's some particular property of our object. What do we have to do to something to move it 1 meter? We have to give it energy. So that must mean that the area under our line represents the amount of energy stored when we raise our mass to some height. And we know that we label energy as joules. Now remember that we talked about 1 calorie being the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius? We also know that there's 4.18 joules of energy in 1 calorie. Did you ever wonder what 1 joule was equal to? Probably not, but I'm going to tell you anyway. 1 joule of energy is defined as the amount of energy that it takes to move an object 1 meter when you apply 1 Newton of force. Nice. So what does that mean in terms of our graph? This graph is specifically looking at gravitational potential energy. So E is the gravitational potential energy in this example. The force is specifically the force of gravity, and the distance we moved, the mass, was the height above the surface. So this graph gives us a nice little equation to determine the amount of gravitational potential energy stored in a mass at any given height. But what if we don't have a force sensor handy to measure the force? Remember that we know that the force of gravity can be found by taking the mass times the gravitational constant. So we can also write the gravitational potential energy is equal to the mass times the gravitational constant times the height above the surface. So if you missed it, you do have a summary that is assigned to you. So for summarizing a lab, you need one sentence for each of the following. You need an introduction that includes the title of the lab, the variables, and your partners. This all needs to be in the first sentence. A very short summary of the procedure. Don't include all of the steps. I know what the steps are. You have that in your lab. I want you to summarize very succinctly what it was that we did in our lab to get our data. And then a sentence talking about the relationship. This is linear, right? This is a straight line. Talk about the slope. Why doesn't the slope go up or down? Why is it a horizontal slope? One sentence talking about the y-intercept. What does it represent about our mass? Now this next one might take you a couple sentences. You want to talk about the meaning of the area under the curve. And when we say curve, we're talking about the line on our graph down to the 0 on the x-axis. So from the origin of the x-axis up to our line, what is the meaning of the area under that curve? And then write a sentence talking about the equation that we derived from that area. Our area was a triangle, so base times height. What does that mean in terms of our variables, in terms of our mass and our force and our height? And then one big summary sentence. Okay, take all of it in, make one big summary.